Hello and a warm welcome to you all. It's a pleasure to have you here today, and I'm excited to introduce the novel topic of multi-band direct microwave sampling on behalf of Teledyne E2V and in collaboration with the IEEE. Over the course of this next 45 minutes or so, you'll learn of unique design possibilities just around the corner, of capabilities leveraging a handful of recent technical enablers that I'll summarise shortly. We're not there yet, but steady and encouraging progress continues apace. So lean in as I draw back the curtain on how this company, a company with over half a century of microwave innovations behind it, anticipates a decade of unprecedented RF broadband advancement. This story culminates in an experimental multi- or crossband transmitter design to be demonstrated in the second half of 2022. Hello there, I'm Mark Holdaway, your host. I'm an avid and seasoned signal path specialist, a writer and technical content producer. It's a pleasure to have your ear. This short overview covers the concept of multiband direct microwave sampling, a capability only recently made possible with the imminent arrival of new data converters. The talk divides into two convenient segments. Part 1 is a basic introduction to microwave applications. The second part describes the design scenarios for an experimental transmitter. Over the course of this presentation, I hope to establish for you the motivation for a multi-band approach to radio design. We'll explore the microwave RF spectrum, and we'll talk about some of the critical applications that can benefit from multiband techniques. I'll also describe some of the myriad technical advancements that have got us to where we are today. In the second part, I'll detail an experimental multiband direct microwave sampling system. Initially, we'll introduce frequency planning considerations, then we'll take a look at the architectural choices that present themselves. And finally, we'll close with the conclusions so far. So the first segment is about setting the context for this project. I want to introduce you to the rationale behind multiband direct microwave sampling. One significant trend driving efforts to improve spectrum use and efficiency is the ever-increasing demand for data. One forecast from research organisation IDC has global demand reaching 175 zettabytes by 2025. Incidentally, a zettabyte is 1 trillion gigabytes, or for the scientifically minded, that's 10 raised to the power 21 bytes, if you prefer. Estimates suggest that the pandemic, through lockdowns and work from home initiatives, drove a traffic increase in excess of 40% last year alone. The only way to support such growth is through improved infrastructure. Microwave plays a key role since it powers much of existing as well as future planned backhaul capacity due to its attractive low latency combined with its line-of-sight implementation. Meanwhile, there is a burgeoning drive to commercialize space. Notable projects include SpaceX's Starlink, which plans to place several thousand communication satellites in low Earth orbit over the next few years to provide unprecedented global internet coverage. In addition, startups are emerging that might drive global space-derived revenues from their present $400 billion to over $1 trillion within the next decade. In the Earth observation market, ICI, a 6-year-old disruptor, is offering persistent imaging unaffected by cloud cover. Their system enables real-time assessments of both human and naturally occurring environmental dynamics. Now, megatrends may shift markets, but technology advancements enable those shifts to take place. For microwave radios, that innovation charge has been gaining pace and is becoming rapidly apparent. The potential benefits likely to arise by adopting multiband techniques are quite diverse. Simplistically, they include better spectrum efficiency. More importantly, though, is advanced mission flexibility. We expect better economics through improved size, weight and power performance, as well as being derived from that mission flexibility previously mentioned. Moreover, dynamic reconfigurability potentially will help extend operational lifetimes. And finally, with the benefits of the latest big data compute capabilities, increasingly real-time multimodal data aggregation can make better use of every single fly past. Let's take a look at the microwave spectrum. Microwave wavelengths cover 2 decades, from 30 centimeters down to 3 millimeters. At the bottom end, they start just above the UHF band. At the top end, they're bookended by terahertz millimeter wave frequencies. As a generalization, progressing through the microwave spectrum, starting with the 1 gigahertz L band and moving up to the W band at 110 gigahertz, we see beneficial and deleterious effects. For example, data throughput increases. This is a result essentially predicted by Shannon's signaling theory. Also beneficially, antenna size decreases as we move up the spectrum. Channel bandwidth increases, but on the downside, rain fade typically increases with increased frequency, though an attenuation peak does exist around 20 gigahertz. Furthermore, higher power levels may support operation at higher frequencies. Microwave spectrum usage covers a host of applications. The more obvious ones seen here include 5th generation mobile handsets, Internet of Things and legacy mobile bands range up into the C-band, satellite communications, synthetic aperture radar, electronic countermeasures, as well as mobile backhaul extend from L through to the Ka band. E-band is a relatively new backhaul LMDS usage for local to mid-distance line of sight communications. And finally, C-band is widely used in Earth observation applications and has powered, amongst other things, ESA's, the European Space Agency's Sentinel Earth observation satellites over the last decade. When considering RF components, especially data converters, it's fair to say that until recently, most parts only operated in the baseband zone, up to perhaps 500 megahertz, i.e. they were only functional in the first Nyquist zone. This point is discussed in more detail later in this webinar. Broadband parts can only sample at low intermediate frequencies and require heterodyning or up and down conversion techniques for frequency translation. Arguably, this has held back RF radio design and has definitely limited the size, weight and power improvements that the market might expect. Fortunately, package material and semiconductor process improvements are coalescing right now to turbocharge RF innovation. One device is already making an impact, and that's our EV12 DD700. This dual 12-bit DAC samples at 12 gigasamples per second and is arguably the industry's first to support direct sampling RF frequency synthesis. For multiband applications, the DD700 can reach the upper K band. Equally, it can project RF power into the Ka band thanks to its native bandwidth of 25 GHz and its double RF output mode. On-chip precision numerically controlled oscillators and digital up converters round out the specifications list, substantially aiding and simplifying the design of RF software-defined radios. So where will multiband direct microwave sampling prevail in future? This webinar considers one specific multiband application with considerable interest today, driven primarily by climate change and concerns regarding the ongoing human impact within our environment, namely for Earth observation. Multiband operation is not new and has been demonstrated over several decades now. A noteworthy multiband example is the US Navy's Raytheon-designed dual-band radar system. This takes the SPY-3 and VSR combined X and S-band surveillance and target tracking systems, was developed during the mid-noughties and is now in general operation at sea. However, the system relies on traditional heterodyning radio design instead of the direct RF access reviewed here. Let's take a more detailed look at SAR-based Earth observation now. Expanding on the process of applying SAR to Earth observation, this diagram shows the geometry of space-based SAR. Such systems usually offer 3 operating modes, each with their own trade-offs with respect to spatial resolution, acquisition time, and data intensity. The first mode highlighted is so-called scan SAR, where the radar beam is steered repeatedly across swathes of the land to acquire backscatter profiles. Scan SAR offers the largest land swaths capture by a single flyover, but equally this scanning method offers the poorest feature resolution. Strip mapping, on the other hand, uses static antenna beams to scan the land parallel to the direction of satellite travel. This method offers a modest swath size and medium spatial resolution. Finally, spotlight mode offers by far the highest resolution, but it comes at the cost of slow acquisition and elevated data intensity. Obviously, each mode has relative merits depending on the precise nature of the Earth observation survey required. Inspecting the physical characteristics of the various microwave bands, it is apparent that each offers specific operational advantages. Shorter wavelengths intuitively yield fine resolution imagery for better object identification. However, the longer wavelengths associated with P and L band operation are better at penetrating the Earth's surface to interrogate its underlying morphology. Moreover, being able to see beneath the tree canopy can be the key in densely forested corners of our planet, which is equally most readily achieved within the P band. A typical SAR mission, as exemplified by ESA's Sentinel-1 satellite, is illustrated here. The satellite deploys a C-band SAR with a center frequency at 5.4 GHz. Sentinel-1 provides 4 distinct scanning modes, shown here, which allows the system to swap from wave measurement over sea to interferometry or other scan methods over land. The first mode shown is a multi-spot wave mode that measures sea characteristics across a 200 km² area. The second mode is a default over land, which produces interferometric swaths over 250 km wide. The strip swath offers a larger increased swept resolution scan over 375 km, and finally the extra wide swath scan provides fast acquisition, lower res imagery. Sentinel-1 offers dual horizontal and vertical polarization radar. It is armed with a single channel transmit for horizontal and vertical polarization, with a clever dual receiver, one each for receiving the returned horizontal and vertically polarized signals. Just a quick comment on surface interferometry. Interferometry is a method to interrogate surface structure, the topology of the ground essentially, which enables us to determine remotely essentially the ground contour lines, the lines that you would normally find on a map showing elevation. This view here shows the volcano of Kilauea in Hawaii, the world's second most active volcano, I believe. And in this image you can see the result of recent eruption, complete with lava flows, and this was back in 2018. To the untrained eye, this image may seem a little confusing. The interferogram shows ground topology, which is missing from a conventional 2D imaged object. In this case, X-band interferometry information is overlaid upon an existing survey image. The volcano is seen centered in the image, and the imaged area covered is approximately a square 9 by 13 kilometers in size. This approach to Earth observation highlights the potential benefits of combining multiband radar systems in real-time data collection activities. Another example of multiband operation comes from the SETHI experimental airborne radar system. This is a French design program. It's been developed over more than 15 years now and has undergone several component refreshes throughout its lifetime. SETHI uses a host of sensors, including multiple devices operating in the visible spectrum. However, SETHI's versatility is derived primarily from the myriad of radar modes it supports. These include VHF, 1.3, 9.5, 10, and most recently 16.5 GHz systems. The adjacent image shown here details land use in Andalusia in Spain. In the uppermost segment, it reveals surface characteristics as seen from the X-band radar system, and subsurface detail is revealed below, which has been derived from the L-band system. This final Earth observation image shows a global vegetational optical depth survey. The plot is compiled from a host of different data sources. In their paper, the researchers identified the challenges of building long-term VOD surveys within the constraints of current systems, but they further show how there is good correlation across datasets, often imaged at different wavelengths within the microwave bands. They point to a limitation when attempting to particularly combine L-band data, despite its obvious value in tree cover assessment. The problems appear to stem from the fact of essentially quality issues with regards to the persistence of coverage. This weakness points to further scientific demand for more comprehensive multiband satellite radar coverage in future. The potential benefits arising from multiband operation in SAR systems include better range resolution, primarily working within the KU band. KU band operates with smaller antennas and can thus use active electronically steerable antenna arrays. In addition, smaller antennas mean single pass interferometry can become practically installed in far more airframes. Finally, quadrature polarization from small antennas enables comprehensive RF backscatter extraction, enhancing real-time land use classification. Finally, let's take a look at some of the important RF enabling technologies leading us towards a multi-band direct microwave sampling capability. So first up, filters, mixers and power splitters. Passive frequency control components are a foundational design element in all radio systems. They ultimately establish the radio interference and rejection performance capabilities. Moreover, their performance in terms of cutoff and passband steepness largely defines operational parameters of next generation systems. This is an example of an RF power splitter provided from RS microwave components. This triplexer provides 3 distinct passbands specifically defined for the L, S and C bands. The attenuation characteristics are clearly shown on the right hand side. Now it's time to turn the spotlight onto active circuits and semiconductor technologies in general. RF power amplifiers continuously improve, demonstrated by this latest 30-watt gallium nitride PA released earlier this year. It's an electronically switched dual-band device working in both the S and X bands and provides more than 20 decibels of gain. The company claims that their dual device exceeds the best-in-class performance of similarly specified single-band PAs. The Corvo dual-band preamplifier shown here has attenuation characteristics with minimum attenuation falling in the S band depicted in blue and the X band shown here in red. This important chart flags the progress of semiconductor figure of merit for two important technology paths. To the left is the deep submicron MOSFET trajectory. As gate lengths shrink, Fmax increases up to a peak seen occurring at the 28 nanometer node. Unfortunately, below 28 nanometers, Fmax tails off rapidly. As a result, conventional CMOS processes no longer sustain a roadmap to ever higher microwave and millimeter wave operation. Fortunately, research focused on heterojunction bipolar transistors, or HBTs, built on silicon germanium provides a new path forward. And while feature size may limit integration densities, HBTs clearly offer a path to Fmaxes beyond half a terahertz. The secret to future multiband DMS lies with the judicious application of HBTs. Teledyne E2V has worked to exploit their microwave expertise to develop increasingly fast broadband capabilities for data converters, both analog to digital and digital to analog. Developments include the commercialization of several generations of products based on BiCMOS HBTs. FinFETs have challenged logic designers in recent years. Equally, the mixed signal design skills necessary to exploit HBTs in highly integrated, high dynamic range converters present a steep and rocky learning curve. Device behavior is hard to simulate and is highly sensitive to parasitic elements introduced at the packaging stage. Moreover, designs naturally tend to oscillate. Such design efforts often feel more akin to lion taming, to be honest. Over the past 25 years, Teledyne E2V has managed to migrate converter technology ever closer to the antenna, with the ultimate goal of directly digitizing antenna signals. Instantaneous bandwidths have risen all the while, to the point today where Ka band frequency synthesis is now possible. The goals of Teledyne E2V's DMS push include agile, multiband operation, software reprogrammability, and improved size, weight, and power performance. We're making excellent progress on the RF transmitter, evidenced by the new 25 GHz bandwidth EV12 DD700. On the receiver side, ADC developments typically lag those of DACs by anywhere between 2 and 5 years. Our latest state-of-the-art product, the EV12 AQ600, introduced 18 months ago approximately, features 6 GHz bandwidth, can sample at a maximum 6.4 gigasamples per second, featuring a 3.2 GHz instantaneous bandwidth. The RF converter portfolio is soon to be augmented by a unique single-channel microwave sampler device, complementing the DAC, designated the EV10XXX here, offering a 3 dB bandwidth of up to 28 GHz with useful performance all the way across the full Ka band. The industry-first broadband microwave sampler shown here is based on system-in-package technology. 3 unique high-performance dies are assembled using a modern substrate material to minimize circuit parasitics and deliver a unique small-footprint microwave sampling solution. Each SIP element exploits the best process option for its role within the signal path. At the front end, we use BiCMOS for the microwave track and hold amplifier. 28 nanometer RF CMOS is deployed for the ADC pre-processing and quantization circuits. And finally, bulk digital CMOS is used for the signal processing and serialization blocks. And here is the completed system in package solution. To close the book on multiband DMS technology enablers, the story would not be complete without mentioning the importance of powerful FPGAs that implement fast cycle DSP and the supporting fast memories required. Moreover, the latest package materials and assembly techniques help to both improve performance, ensure thermal stability, and ensure that the system economics stack up. Finally, the rapidly evolving science of meta antennas and the ability of fast digital signal processing to support active electronically scanned antenna arrays is also helping to accelerate the availability of multiband DMS. Now I'd like to move on to the second half of this seminar to talk a little bit about digital transmitter design considerations. And first up, let's take a look at multiband frequency planning. And this really is primarily a discussion about Nyquist zones and direct sampling technology. Frequency planning is a key aspect of radio system design, not least because of global standardization and licensing of RF spectrum, driven from a need for interference suppression and optimal frequency reuse. Frequency planning requires a fundamental understanding of the process of frequency mixing induced by modulation. Moreover, planning should be viewed in the context of band-limited signals, component non-idealities, and as well an understanding how broadband sampled signals are transformed without filtering into multiple Nyquist zones. The simple case shown here illustrates a baseband signal appearing on the left, transformed through Nyquist sampling to subsequently appear as upconverted synthetic signal power delivered into every Nyquist zone. Consider the output characteristics of the EV12 DD700 plotted here. Signal power is delivered across a frequency range spanning a few gigahertz up to beyond 24 gig. The device generates an instantaneous signal bandwidth of 6 gig. The various microwave bands, when overlaid on the plot, indicate that, in principle, this stack provides output modes capable of projecting synthetic RF well into the uppermost Ka band. You can see that the DAC projects signal power into any of the 5 Nyquist zones illustrated here. Establishing a frequency plan requires a clear objective. The primary aim with this prototype is to deliver a multi-band direct microwave sampling transmit path. So which DAC output mode best suits that task? Non-return to zero, RF, or 2RF? Well, it may not be immediately obvious, but the 2RF mode does not feature in this development. Non-return to zero mode offers easily the highest output power in the first Nyquist zone, and it also extends into the C-band. The broadband RF mode offers excellent output across second and third Nyquist zones, therefore making it suitable for application from S through to Ku band. And finally, while the double RF or 2RF mode provides excellent access to K and even lower Ka band signals, It is clearly an inferior choice for use in the first and second Nyquist zones, given the rapid attenuation seen in the L and X bands. Moreover, 2RF operation requires a double rate sample clock, meaning that lower microwave frequency components are lost. The beneficial combination of non-return to zero and RF modes provided by the dual-channel 12DD700 demonstrates a workable multiband range that extends from DC all the way up to 18 GHz and beyond, meaning that for the first time direct RF access is possible across 3 Nyquist zones covering L to Ku bands. Turning now to consider specific microwave frequencies for our concept design. Our intention is to design a system able to operate continuously from the L to the Ka band. We've seen that operationally, based on the delivered performance of the target DAC, that best operation should focus on NRZ and RF modes, operating essentially within the Nyquist zone 1 to 3. The multiband design will therefore define the following operating parameters. In the L band, a center frequency of 1.3 GHz and a bandwidth of 400 MHz. In the X band, a center frequency of 9.5 GHz and a bandwidth of 1200 MHz. In the Ku band, center frequency at 17.2 GHz with a bandwidth of 200 MHz. And finally in the Ka band, center frequency of 35.75 GHz and a bandwidth of 500 MHz. We've seen already with our frequency planning relative to the output modes of the DAC that we can essentially reach from the L to the Ku band as highlighted here. But one observation to make is that within the context of the 12DD700 dual DAC, Ka band access will only be achieved through using an upconversion system. Following considerations of the best DAC output modes or modes, the radio design can now be considered in more detail. Two choices for multiband operations suggest themselves. The first is a traditional design using a baseband radio approach combined with heterodyning or upconversion. Alternatively, a second approach is a direct RF access approach enabled by the broadband 12DD700 performance. Let's take a look at the first, more traditional approach. Here we're using the DAC in RF output mode, providing a number of advantages as follows: high output power, good crossband power flatness, the ability to simultaneously sample all bands, and additionally a straightforward approach for beam steering. The upconverted signal power translated into second and third Nyquist zones is clearly visible in the plots on the right. Perhaps unsurprisingly, this design requires extensive frequency control components to isolate individual microwave bands, leading to a very complex bill of materials, plus the added costs and system complexity. It's likely that an entire system would also prove challenging to lay out and certainly not advance the drive towards size, weight and power improvements overall. The synthetic upconverted signal power translated into the second and third Nyquist zones is shown quite clearly in the plots on the right here. Note that each RF band is clearly discernible with good spacing between them across this 12 gig signal frequency range. The uppermost Ka band signals fold down from 35.75 gig, leading to mirror image versions appearing centered around 12 gigahertz. This image highlights the complexity that we've hinted at of the resulting system. Note that only one RF channel appears here to simplify the diagram, but the complete solution does require the second channel to be in place. Every component after the DAC doubles up as a result. This creates a frequency control bill of materials comprising 10 filters per channel and 3 mixers per channel. In total, that's 26 components, not counting the power splitters and ballons. So next up is the novel direct RF access approach. In this case, the individual channels operate in different output modes, which is a clear advantage having the 2 discrete DAC channels on hand to exploit. One channel is set for non-return to zero, the second channel being set to RF operation. Because of DAC limitations, one of the target microwave bands, namely Ka, as we've previously mentioned, has to be accessed conventionally by an up converter. Lower frequencies, however, are covered by direct RF sampling. This approach matches a number of the pros previously outlined in the first approach, including broad synthetic power projection, simultaneous multiband channel selection, but the standout benefit of this approach is a substantial reduction in the entire frequency control bill of materials. So how does this first configuration function? Well, the first DAC channel is focused on operating in the first Nyquist zone, and as you can see, receives the down-converted Ka band as well as the L band signal. For the second channel, operating in RF mode, it translates synthetic signal power into either Nyquist zone 2 or 3 for both the X and Ku bands. This factor further enhances frequency component management, since now the radio designer can choose which of the alias band signals to select in either Nyquist zone. Moreover, it may help relax some of the filter requirements. In this concept, we chose to directly access the X band through Nyquist zone 2 and the Ku band in the third Nyquist zone, as shown. For this use case, both channels are fully populated here in the diagram with their frequency control elements. The dramatic reduction to the bill of material is immediately apparent. The upper non-return to zero channel handles both the lowest and highest frequency bands, that is the L and Ka band. You can see that the Ka band is supplied by the up converter. The lower RF channel provides direct access to both X and Ku bands. Remarkably, a total of only 6 filters and 1 mixer provide the complete multiband frequency control elements. Let's compare these approaches side by side. The BOM simplification becomes immediately obvious. The frequency control components drops from 30 for the traditional heterodyne design to only 10 units for the direct RF access solution. The ability to combine multiple radar bands, especially in space missions, has been highlighted in the last year with the recent launch of Sentinel 6, which is a collaborative project managed by EUMETSAT. The instrument cluster of Sentinel 6 serves the primary mission of high-performance ocean altimetry, better known as sea level monitoring. Sentinel 6 provides the highest resolution sea level data thus far through its dual-band radar system. Furthermore, onboard instruments permit vertical temperature monitoring in the tropo and stratospheres to help improve long-term weather forecasting outcomes. Sentinel 6, with a launch mass just shy of 1.2 metric tons, is currently being commissioned at an orbit of 1,336 kilometers, with a flyby repeat interval of 10 days. Combined with its sister satellite 6B, by 2030, the world will have aggregated over 40 years of continuous sea level monitoring data, helping humanity keep tabs on the impact of human-driven climate change. Okay, we're on the last leg of this webinar, and it's time to wrap things up. This was a quick dive into the concept of novel multiband direct microwave sampling, an enabling technology for future highly agile software-defined microwave radios. You've seen why the time is right to start thinking more deeply about your future microwave design approaches. There remains some work to be done back at our labs to implement the Direct RF approach that we've outlined here. Nevertheless, this represents novel research. It is not practically proven, but we anticipate system-level results will emerge shortly. Meanwhile, you've learnt that multiband transmit technology already exists in the form of our new EV12 DD700 DAC. Multiband design demands careful frequency planning. On first observation, multiband design may appear somewhat impractical given the demands of frequency control, especially seen through the lens of a traditional heterodyne radio approach. But broadband converters have facilitated direct access and make designs potentially considerably simpler. The dual output DAC that we've illustrated here facilitates a simplified hybrid multiband design. The availability of both non-return to zero and RF modes significantly reduces the filters and mixers required in the system. This helps to produce a less challenging analog design, as well as simplifying the bill of materials and implementation costs. Before parting company, I would just like to highlight the fact that I gathered together in the appendix at the end of this webinar a series of web links to useful online resources. I hope this presentation may have inspired your further interest in geoscience and Earth observation technologies. Thank you so much for your attention. I hope that this webinar has proven both thought-provoking and even at times slightly surprising. There was a lot of ground to cover, and I hope we've done the topic justice and not left you with too many questions. We look forward to returning to this topic and offering you an update of the development program within the next few months, as well as being able to share some measured electrical performance data with you. Once again, thank you for your kind attention during the webinar. I've been Mark Holdaway, and this has been a session focused on the enabling technologies behind delivering a modern digital radio applying multi-band direct microwave sampling on behalf of Teledyne E2V. Thank you and goodbye.